All right, so let's move on to the last reaction of this chapter. So reaction 10, so we call Baeyer-Villiger oxidation. That's the name of reaction. Okay, this is another example of name reaction. And the name reaction, I mean any reaction that have person's name in it. For example, Friedel-Crafts, alkylation, acylation, Diels-Alder reaction. Those are name reaction. Wolff-Kishner, right? Reduction. Right. This one is called Baeyer-Villiger oxidation. Let's see what's going on. So we take aldehyde or ketone and treat it with peroxy acid. All right. So you got, let's say, an ester. So basically, we put I label one oxygen of the peroxy acid in red. That oxygen will insert itself into aldehyde ketone. Really, really interesting how this works, and could be confusing for some of you. Okay, but we can explain how this works. But basically, this is an overall reaction. So the red oxygen there of the peroxy acid insert itself into aldehyde ketone. Okay, the mechanism goes like this. There are multiple mechanisms that I have seen. Okay, that's the one I show you. This I mean is correctly. In the textbook it's slightly different, but I mean you get the same product at the end, just slightly different, like the protonation is different. Okay, all right. So first one I'm going to do this: take the oxygen of aldehyde or ketone carbonyl, attack the proton, so deprotonate that. Okay, this reaction of course is not that favorable, so this is a strong acid, right? This is much weaker, not that favorable, but if you go forward I'll show you why. Okay, the second step is nucleophilic attack. Just take this molecule right here, the rest, right, the conjugate base, attack the carbonyl carbon. All right, now it gets difficult right here, so watch carefully. All right, I'm going to from a double bond right here. I think you guys have seen this many times that we do form double bond here in like acetal formation, imine or enamines formation, right? We form double bond here, and the leaving group has to leave, right? In those you have seen in before earlier. But now, if I'm going to form double bond right here, who's the leaving group? In this case, the leaving group is the alkyl group right here, one of these two alkyl groups. So it leaves and it attack that red oxygen. We call this step right here migration or rearrangement. Okay, so from double bond right here, the carbon in the middle is about to be over octet. So we have to need a leaving group to leave, but we don't have a leaving group. Well, this happened. One of these two alkyl groups will migrate up to the red oxygen of the peroxy acid. Okay, and the leaving group is actually the carboxylate right here, the rest part right here. Okay, this step is irreversible. We can't really go backward in here. Right, that's one of the driving force. All right, forming you learn in next chapter that carboxylate is also stable, highly stable. That's another driving force. All right. Look at this right here. We're not done yet. This guy right here, this compound, this intermediate. This intermediate is weird. Look at the structure. I don't like that. I'm going to redraw it. So that's the structure. What do we have to do with it? Well, it's positively charged right now. Deprotonation. So you would get the neutral compound. Okay. All right, let's practice draw the mechanism together. So all you have to do, I want you to draw on your own first. Pause the video, draw on your own. Look back to the previous slide if you need to get to the product. Okay. All right, now check with me. So MCPPA. So you use this reaction many times now. All right. So it's a type of peroxy acid. So meta-chloro-peroxybenzoic acid. We'll insert one of this oxygen of the peroxy acid into the 5-membered ring, so you get 6-membered ring later. All right, the first step. So I'm going to deprotonate the MCPPA and get protonated species. Okay, and we're gonna now nucleophilic attack. All right, so you get a red oxygen right here. Now the migratory step is right here. First off, forming double bond there. We need a leaving group to leave, but we don't have a leaving group. So take one of these two carbon, either one, they're symmetrical, so either one works. Attack the red carbon, and holding the rest, the carboxylate, leave as carboxylate. Here we go, like that. Okay. All right, look at the cyclic ester right here. So sigma with ring, so I'm not going to draw like that. That's weird. So look like that. All right. Deprotonation, you get to the product. Here we go. All right, that's pretty much it. All right, that's the mechanism. The next video, we're going to talk about the detail, like how this works and how do we use it. Okay. All right.